Hello everyone, welcome back. In the last class we saw that how you can use discretization for a first order function, okay, first order derivative of a function using the one sided formulation and the two sided formulation. We looked at the basically the first order and second order schemes, and we learnt about the different errors that we have due to the discretization. Okay. Today we will go to the general discretization approach, and we also see how we can basically approximate second order derivatives and so on and so forth. Okay. So, let us start where we left. Okay. So, now in the last class we calculated del f by del x at I, okay, but as we discussed we also need to find del 2 f by del x square, okay, and ideally you can find any order derivative using your Taylor series method, right. So, if you use the same discretization I plus 1 and I minus 1. So, right now we are only basically using the uniform mesh, okay. This is 1 to n, and there will be boundary conditions here at 1 and n, and in the interior points you have to approximate the derivatives, right. So, at I you want to calculate, okay. So, you want to calculate the second order derivative. So, what you can do, let us take the point I minus 1, I plus 1 and I. Okay, there is one rule here which I want to tell you, okay, so that if you want to calculate the second order derivative, okay, you need at least 2 plus 1 points, basically n plus 1 points to get the derivative. So, for the first order derivative you need at least 2 points, okay. For the second order derivative you need at least 3 points. Let us say you have the third order derivative, okay, then you need at least 4 points, at least. You can use more points also, then it will give you the more accurate scheme, but at least you need n plus 1 points to in the stencil to calculate the derivative, right. So, here let us see we are taking the 3 points I minus 1, I and I plus 1, right. So, you can take I plus 1 will be I plus, okay, let me use, okay, delta x is okay, okay, f I prime plus delta x square factorial 2 f I double prime plus delta x square x cube factorial 3 f I triple point and so on and so forth. F I minus 1 will be f I, and then will be minus delta x, okay. Why we are doing around I? Because we want to get the gradient at I, we want to calculate the derivative I at I. So, that is why we are writing all this I plus 1 and I minus 1 around I, okay. You might want to basically calculate the derivative at I plus 1, okay, then you have to calculate accordingly, choose the points, and then you have to write the Taylor series expansion around I plus 1, okay. Any point you want to take, you have to write the expansion around that point. So, this will be f I prime plus delta x square factorial 2 f I double prime minus delta x cube y factorial 3 f I triple prime and so on and so forth, okay. This is my 1 and this is my 2. What is the thing that you want to calculate? You want to calculate del 2 f by del x square at I, right, which is nothing but f I double prime, right. So, we need to basically keep this. So, what for that what you do, we will do 1 plus 2, okay. Earlier for the central differentiation scheme of the first order we had done 1 minus 2, right. So, if you do that, this will become f I plus 1 plus f I minus 1 will equal to 2 f I, this would cancel out, okay, and plus this 2 will cancel out. So, that will become del x square f I double prime, and then this would cancel out, okay, and there will be a fourth term also, okay. Let me write that also, there will be one term here. So, that will become 2 into delta x to the power 4 by factorial 4, right, f I prime and plus so on and so forth, right. So, now you collect the term. So, we want to get this. So, this can be written as f I double prime, which will be del to f by del x square, okay, at I would be f I plus 1 minus plus f I minus 1 minus 2 f I by delta x square. Okay, this is the approximation, and what is your truncation error or the leading truncation error? Okay, the minus so 4 3 is 12. Okay, so 12 and delta x square will get cancelled. So delta x square f I to the power 4 prime. Okay, so this is the approximation of your second order derivative, and this is your leading truncation error. Right, you can see that your leading truncation error is order of square. Right. Okay, this can be any derivative. It can be fi double prime, triple prime, fourth prime. What you need to see is that what is the power of your gradient power of your delta x term is there. Okay, that is what it gives you your order of accuracy. So, this is raised to the power 2. So, this is a second order accurate scheme. Okay. So, we got the derivative for the approximation for the second order derivative, right. We can also basically use that to do the I mean in a different way. So, what you can do, let us say you can write del to f by del x square at I. So, you can use the forward differencing approach like we have done earlier. Okay. So, that will become okay, right, double prime I will be f I plus 1 forward differencing prime, because this is a double prime. So, this will become first 1 prime minus f I prime by delta x, right. So, this is we use the forward differencing here. Okay. Now, for this first prime you use the backward differencing. So, you can write f I plus 1 prime. If you use the backward differencing, that will become f I plus 1 minus f I backward differencing around I plus 1, right, will delta x, and f I prime will become f I minus f I minus 1 by delta x, right. So, this will become f I plus 1 minus f I by delta x minus f I minus f I minus 1 by delta x, and that this will become f I plus 1 plus f I minus 1 minus f I by delta x square. Okay. So, the same formulation as we have derived earlier. Okay. This one. So, you can do either the Taylor series expansion around f I around the first order derivative, or you can do the Taylor series expansion around the function, and you will get the same thing. Okay. And this has got the truncation error of delta x square. Okay. So, order of accuracy is 2. Okay. The reason I have shown you two different approaches to get the second order derivative is that here you can see that first we use the first forward derivative, okay, and then use the backward differencing here, okay, and we got the formulation which gives you the 3-point stencil formula for the second order derivative, and also give you the this delta x square as the discretization error. Okay. So, we will be using this when we go to this 2-step schemes in some of the like Richter-Meyer scheme and some other schemes, McCormack scheme. Okay, you will see that these kind of formulations are used, where you first use the first forward differencing and then use the backward differencing to gain some stability, right. So, that will be discussing in the future. Okay. So, now we have basically got this the first order derivative and second order derivative. You can also get, if you want, del q f by del x q and so on and so forth by using the different Taylor series expansions. We will not get into those details, because ultimately the maximum derivative that we need to calculate equation is the second order derivative. Okay. Now, this is formulation that we have done by deriving the Taylor series expansion. But let us say if I have this grid, okay, and this is I and I plus 1 and I minus 1, okay, and this let us say I plus 2 and I minus 2. Let us say I want to get the first order derivative by using these 3 I plus 1 and I plus 2, okay, or maybe this 4 I minus 1, I plus 1 and I plus 2. And how do you get that? So, there should be a general approach to get those derivatives easily. Okay. You can of course go through the tedious Taylor series way and get those I mean manipulate those different functions, like what we are doing here is, for example, we are basically doing 1 plus 2, sometimes you have to do 1 minus 2. If you have 3-4 different Taylor series, you have basically arrange it in such a way that the terms that you want, the derivatives that you want remain and the others get cancelled out, right. But there is a more general approach that you can use to basically solve these problems, and that is what we are going to do now. Is it is called the general discretization approach. Okay. You can calculate any order derivative using this approach, right. So, how do you do that? Let me just resolve the same problem that we had done earlier, the central referencing scheme using the general discretization approach. So, what we do? So, we want to calculate the value of phi f I prime, okay, or basically del f by del x at I, okay, using these 3 points I plus 1 and I minus 1. Okay. So, what we will do, we will write this in terms of those 3 points. Okay. So, this will be A f I plus 1, okay, and plus B f I and plus C f I minus 1 by, you can write like that, but you know that this is delta x here. So, you can write here delta x here as well, right. And now, the goal is to find out what is the value of A, B and C, okay, so that you can get this del f by del xi, right. If let us say you have more points, let us say you want to take I plus 2 also, okay, you might want to add D I plus f I plus 2, and then you have to find out f A, B, C and D, all of these, right. So, let us say right now we are just finding this A, B and C, okay. So, now you expand f I plus 1, this is also Taylor series only, but it is a more general approach. So, this will become f I plus delta x f I prime, okay, plus delta x square f I double prime and so on and so forth. F I minus 1 is basically f I minus delta x f I prime plus delta x square by factorial 2 f I double prime and plus, right. Now, use this is my equation A. So, if you look at the equation A, okay, if you closely look at equation A, so the multiplication of f I on the left side, there is no multiplication, now there is no f I term, right. So, the f I, the coefficient of, if I call it coefficient of f I is equal to 0, right. Coefficient of f I prime is equal to 1, right, because this is what we want to calculate. So, what we are doing, we are basically approximating, or basically we are equating the left hand side to the right hand side, okay. And the third, because we need 3 equations. So, coefficient of f I double prime is also 0, right. So, use those, okay. So, you multiply this by A, multiply this by C, right, this is A and this is C and B is already there with f I, right. So, we will multiply this and then we will approximate all these 3 terms, right. So, if you just take f I, so there is one A f I, C f I and B f I. So, that is basically A plus B plus C f I is equal to 0, right. So, that means A plus B plus C equal to 0. So, that is the first equation that we got. Second is coefficient of f I prime is equal to 1, right. So, collect the f I prime term. So, basically this is A delta x plus there is no f I term here, plus C delta x, okay, Now, this will be C and that will be minus delta x, minus C delta x by delta x equal to 0. Okay, delta x is here also, but delta x cannot go to 0. So, this is basically A minus C is equal to 0. Okay. Just let me see. Okay, just this will be equal to 1. Okay, this is equal to 1. And the third term is, now we are approximating the Fi double prime, these coefficients. So, that will become A delta x square by factorial 2. Okay, I will take the factorial 2 later, and plus C delta x square by factorial 2 into delta x is equal to 0. So, you can ignore this delta x in factorial 2, that will give you A plus C is equal to 0, right. So, if you solve this, okay, this is equation 1, 2 and 3. You have 3 equations and 3 variables A, B and C, and you can easily calculate that. Okay. So, if you use 2 plus 3, okay, so that will become 2A is equal to 1, A will be 1 by 2, okay, and C will be minus A. So, C will be minus A is equal to minus 1 by 2, and then B will, from using 1, B will become 0, right. Now, let us put this, all these things here in this equation A, right. So, final equation will be del f by del x at I is equal to 1 by 2 Fi plus 1 plus 0 Fi minus 1 by 2 Fi minus 1 by delta x, right. That is basically Fi plus 1 minus Fi minus 1 by 2 delta x. What is this? This is nothing but your central differencing formula, right. So, by just finding the coefficients A, B and C and using the Taylor series, we got the central differencing formula. Now, this looks very trivial because you can easily calculate the central differencing formula, but basically you can use this general discretization approach to find approximation of derivative using any discretization points. Okay, you can use I minus 1, I plus 1, I plus 2 and so on and so forth. I will show you some examples. Okay. So, before that it is important to remember, as we have discussed earlier, that if you want to get the derivative and the derivative, you need at least n plus 1 point stencil. Okay. This is the number of points. If you want to get second derivative, you need at least 3 point stencil. If you want to get third derivative, you will need at least 4 point derivative, and you have n Taylor series expansion, because you may not need to because there will be one point which is the central point around which you are trying to find out the derivative. So, you do not need expansion there, but all other points you need to have the expansion around the central point. However, it is possible to increase the size of order of accuracy by increasing the stencil size, right. So, right now what we have done, we have taken I plus 1 and I minus 1 to get the derivative del f by del x at I, right, but nothing stops you from considering I plus 2 and I minus 2 also. This is the advantage of the finite difference, right, that basically you can use the stencil size as big as you want, okay, to get your gradients as best as you can, right. This you cannot do in finite volume. Okay. There these points are not well defined or not in order like I plus 1, I plus 2, I minus 1 and I minus 2 and so on and so forth, right. So, you cannot use this scheme, but let us say you want to use these 5 points and calculate the del f by del x equal to I. So, how do you do that, right. So, you can use this general discretization approach. Okay. So, you can write your expression phi I prime as A phi I plus 1, B phi I plus 2, C phi I. So, we have 5 points, okay, I plus 1, I plus 2, I minus 1 and I minus 2, okay, and divide by h, right. So, this is your formulation. Okay. Now, what you can do, you can use the Taylor series expansion around I plus 1, I plus 2, I minus 2 and I minus 1, okay, and get the 5 equations. You have to basically approximate the derivative of basically phi I prime, phi I double prime, phi I triple prime and phi I 4 prime. Okay, then you will get 5 equations and 5 unknowns, you can solve it. a more smarter way to solve that is basically use the symmetry, right, if you have points on the either side. Okay. In that case, for the first order derivative, you can, like we have done for the this case, if you recall, this b goes to 0, right, the fi point goes to 0. So, if you can use that symmetry, okay, you can write in terms of c will become 0, okay, and a will become minus e and b will become minus d, right. So, your equation will become phi I prime will be a phi I plus 1, okay, and minus phi I minus 1 by delta x or h, whatever you want to write, and plus b phi I plus 2 minus phi I minus 2 by delta x, right. We have used the property of the symmetry, right, and now your task is to find a and b. So, how do you do that? You can use phi I plus 1 is equal to phi I plus delta x phi I prime plus delta x square by factorial 2 phi I double prime and so on and so forth. Phi I minus 1 is equal to phi I minus delta x phi I prime plus delta x square by factorial 2 phi I double prime. Okay, I will write one more time, delta x cube by factorial 3 phi I triple prime phi I triple prime, and you can write more terms, okay. And similarly, you have phi I plus 2. So, what is phi I plus 2? This is basically phi x plus 2 delta x, right, which is what is, this is phi I plus 2. So, if you expand it around x, so you will have 2 delta x instead of delta x. This we are expanding everything around I. So, that is very important to remember. We want to get phi prime at I. So, we need to expand everything around I plus 2 delta x phi prime plus 2 delta x square by factorial 2 phi I double prime plus 2 delta x cube by factorial 3 phi I triple prime, okay. And similarly, phi I minus 2 will be phi I minus 2 delta x phi I prime plus 2 delta x square to phi I double prime and minus 2 delta x cube by factorial 3 phi I triple prime, right. So, now we have what we have to coefficients you need to collect here. So, one is that phi I prime, okay. So, this is multiplied by these both multiplied by, okay, this is multiplied by a, this is multiplied by minus a, okay, this is multiplied by b and this is multiplied by minus b, right. So, we are now trying to calculate the terms, okay. So, you can do that a phi I plus 1. So, let us collect the phi I prime term, okay, because we have already used the symmetry. So, you can see that this phi I time terms are already going 0. So, you have already ensured that phi I coefficients of phi I are 0 by using symmetry, okay. So, that we do not need. So, what we want the coefficients of phi I prime that will give you 1, right, because left hand side is 1. So, if you do that, okay, so coefficient of phi I prime we want to calculate. So, that will become a, delta x is already there. So, I am not writing that, okay. So, a plus a, but that will become 2a, right, and now phi I plus 2 or phi I minus 2. So, this is I plus 2 and this is I minus 2. So, that will become 2b and this will 4b, right, 2a plus 4b is equal to, right, I hope I am correct, is equal to 1, right. Now, we have to basically collect the terms of, if you look at the phi I double prime, okay, that is going to 0, but that we have already ensured by doing the symmetry. That is how you got I equal to basically e equal to minus a and d equal to minus b, right. So, the last term that we need to see is phi I triple prime is going to 0, right. We have two variables, so we need two equations, right. So, if you do that, so this is delta x cube by factorial 3, right. So, this is a and a, so that will be 2a by factorial 3, and then be plus this is b and this is b. So, 2 cube is 8, 2 into 8 b by factorial 3 is equal to 0, right. So, now you have got a plus 8b equal to 0. So, 2a plus 4b equal to 1 and a plus 8b is equal to 0, right. So, this is your, I can call this equation 1 and this is equation 2, right. I hope I have not made many mistake. The factorial 3 you can, I mean that can get away, and this is a plus 8b. So, now you do 2 into 2 minus 1. So, that will become 16b minus 4b is equal to minus 1. So, b equal to minus 1 by 12, right. And from 2, a will be minus 8b, this will be 8 by 12, which is basically 2 by 3. So, this is 2 by 3, right. So, your phi I prime will become 2 by 3 phi I plus 1 minus phi I minus 1 by delta x, and minus 1 by 12 phi I plus 2 minus phi I minus 2 by delta x, right. Just by using our Taylor series, we got the values of this, and this if you mean careful, I mean if you see this, the order of accuracy, this will become higher, because this will be next term will be delta x to the power 4, right, and then you are dividing everything by delta x. So, that will become delta x cube. Okay, please go back and check. Okay. So, that should your order of accuracy is increased by increasing the stencil size. Okay. So, what we did, we basically used the higher coefficients and equated the higher coefficients, and we basically increase the order of accuracy by increasing the stencil size and cancelling the higher order derivative terms. So, in this case we cancel the third order derivative terms, right. Here we made use of that, and we got the values, right. Similarly, you can basically use any complicated thing. For example, if you want to calculate this del k u by del x q, and the node points are given as I minus 2, I minus 1, I and I plus 1, right. So, you want to calculate the third derivative. So, what you will do, you write u I minus 2, okay, and that will become u I minus 2 delta x u I prime, okay, u and phi does not matter, okay, plus 2 delta x square factorial 2, okay, u I double prime, so on and so forth. Similarly, u I minus 1 you use, okay. This is the third order derivative, so you have to write at least the third term, okay. So, let me write one more term, okay. So, that will become 2 delta x cube, this will be negative, minus by factorial 3 u I triple prime, and so on and so forth, okay, minus delta x u I prime plus delta x square by factorial 2 u I double prime minus delta x cube by factorial 3 u I triple prime, and so on and so forth. And similarly, you have u I plus 1 be u I plus delta x u I prime plus delta x square factorial 2 u I prime double prime minus plus delta x cube by factorial 3 u I triple prime, and so on and so forth, right. And what is the thing that you want to get? You want to get u I triple prime, right. This is the thing that you want to get, and what you will do, you will write a u I minus 2 plus b u I minus 1 plus c u I plus d u I plus 1 by, you can write, I mean it will be delta x cube here, but even if you do not write delta x cube, you will automatically get that delta x cube here, right. This is the third derivative. So, that will be delta x cube. The second order we had delta x square, in the first order we had the delta x. Put these values, all this Taylor series expansion, multiply this by a, this by b, and this by d, right, and compare the coefficients of basically ui, okay, which is 0, coefficient of ui prime, which is also 0, ui double prime, which is also 0, and ui triple prime, which is basically equal to 1, right. And when you use this, basically of the 4 variables and 4 equations, ultimately you will get those equations, and what you can do, you can basically, so these are the expressions that you are going to get, okay. These are basically these 4 expressions, okay. So, what we have done, we have solved this a x equal to b, okay, because this becomes the complicated problem. So, this is basically a, b, c and d, right. So, this is basically, if you equate that, this is a plus b plus c plus d, because this is the coefficient of phi I, right. So, that will become 0. Similarly, this is phi I prime, okay, minus 2, minus 1, 0 and 1, okay. You can go back and please work this out. Similarly, for phi I double prime, we have 4, 1, 0, 1, and that will also 0, and the last one will be 1 and 1 and 1 and 1, okay. This is the phi I triple prime, and this value is 1, and because you have a factorial 3, so that will become 6 here, okay. So, you can use write any simple program, or you can solve it also manually if you want, and you can get the values of a, b, c and d, and this is the value that you will get, okay. Plug those values into this expression that we have here, and you can calculate the third order derivative using these stencils points, okay. Similarly, there is one more homework I want to give you, please go back and work this out. So, here what we want to do, derive an expression for the second derivative at I equal to 2. So, here you have to basically, this is I equal to 1, 2, 3, okay, 4, 5 and so on and so forth, right. So, or you can write I plus 1, I plus 2, I plus 3 and I plus 4, okay. So, we are using these stencils point, and you want to basically calculate the second derivative. So, you want to calculate del to f by del x square at I plus 1, right. This is what you want to calculate, right. So, what you need to do, at I you need to write the Taylor series around I plus 1, I plus 2 you need to write a Taylor series around I plus 1, I plus 3 you want to need to write Taylor series around I plus 1, I plus 4 you need to write Taylor series around I plus 1, and for this also, and then compare the coefficients, right. For example, okay, I have shown here, okay. So, you can write 1, 3, 4, 5 around everything around 2, okay. Compare the coefficients, okay. You will have 5 coefficients here this time, and then you solve it and you will get the values of a, b, c, d and e, okay. So, this is the general discretization approach. You can for practice you can take any number of stencil points, okay, and try to get the derivative that you want, right. So, with this we will stop here. In the next class what we will do, we will see can we get the higher, I mean better order approximation or better order of accuracy using the same stencil point, okay. So, those kind of schemes are called the compact schemes, okay. So, those are kind of implicit schemes, but they give you better accuracy using the same stencil. So, we will look into that schemes, and then we will also look at what happens when your mesh becomes non-uniform, right. So, we will discuss those things in the next class. Please practice about this general discretization approach, and that will be very useful for your understanding of the finite difference approach in CFD. Thank you very much.